Okay, good afternoon, everyone. Today we'll begin our journey into electronics, analysis of electronic devices. And so in chapter 1, we will talk about diodes, but for today, I want to talk about the differences. I will begin with the differences between circuit analysis of the elements we did in 201 versus the electronic devices that we will look at in 321. So let's go to the class notebook. And let's see. Okay, should be visible. All right, electronics. Let's take a step back and think about 201. We learned about circuit analysis techniques with regards to 3 elements, right? We had resistors, inductors, and capacitors, R, L, and C. So all 3 of these are classified as linear elements. Okay, linear elements. And the reason we say they are linear elements is because the voltage and current for these elements have a linear relationship. Ohm's law, V equals IR. If you increase or decrease the voltage that is applied to a resistor, the current would also increase or decrease proportionally. And vice versa. If you increase or decrease the current, voltage would increase or decrease proportionally. Right? They have a linear relationship. So hence, they are called linear elements and linear circuits. So V versus I is linear. The analysis of such circuits uses analytical methods. And so we say we use analytical approach to solve for linear circuits. Now, analytical in this case means an exact solution. Okay, you have an equation, V equals IR, for example. If you know the resistance, if you know the voltage, you plug in the values, you can calculate the current that is flowing through. If you know the current, you can calculate the voltage and vice versa. And so the solution is exact. Electronic devices, on the other hand, are nonlinear. The voltage and current for nonlinear, voltage and current relationships for electronic devices do not have a linear relationship. If you increase the voltage for a diode, for example, the current is not going to increase. Not necessarily. Okay. Same thing for a transistor, same thing with the FET. No matter what kind of electronic device it is, it does not have a linear relationship. So all of these are classified as nonlinear devices. Nonlinear devices. And we use numerical methods to analyze these circuits. And numerical methods do not provide an exact answer or an exact solution. These are approximate. Okay. So again, nonlinear devices, we use a numerical approach, we use numerical methods. Numerical methods basically provide an approximate answer. And the reason is we use several different models for each device. So I would say there are several models for each device. Depending on our use case scenario, we can pick and choose which models we'd like to use for our circuit. And I can make an analogy with a real life scenario. How many of you have been to like job interviews, whether for internships or whether for anything for that matter? and where you might have encountered a question which says, tell me about yourself, right? Some of you have, I see lots of nods, right? It's a very common scenario. It happens all too often. So you should be prepared. If you have never ever thought about it, you should be prepared to talk about yourself. So just going on a little bit of a tangent, you should be able to describe yourself in 5 sentences. Subjective, qualitative description that does not appear on the resume. That is what the interviewer is looking for. They want to know something about you that is not on the resume. Okay. If you're just repeating what's on the resume, that's also fine. Any at least maybe 50% of your description. Sometimes people might just show up to interviews without reading the resume. They're just like, moment, oh yeah, here's the candidate waiting for you. Oh, here's the resume. You're gonna scan through it. Then they come in and they'll say, okay, tell me about yourself. It happens. Okay. So the point is you should be prepared to talk about yourself. So if I ask you the question right now, tell me about yourself in 5 sentences, would you be able to do it? I'm not asking you to, but I'm saying just inside your own head, maybe, if I give you 5 minutes or 10 minutes, yeah, you'd be able to describe yourself. If I say, describe yourself in 10 words, what if I say, describe yourself in 5 words, 2 words, or 1 word? It might get progressively harder, but all of those descriptions would be true. It might not describe you completely, but they are still true. Under certain conditions and certain places around certain people, those descriptions would be true. In the same way, we would use electronic devices. We would use several different models to describe our devices, and they would all be true. Depending on the circuit conditions, depending on the environment we are using them, depending on our end application usage, we would pick and choose which models we want to use. And hence the answers would always be approximate. They would not describe the working of a device under all conditions. For instance, if I'm analyzing a diode circuit, for instance, and this is something that we will learn, I could use a model that is known as the ideal diode model, which simply describes as the diode being either on or off, like a light switch, on or off. That's it. So diode is either on or off. The voltage and the current values that I would obtain using such a model would not be the most accurate because I'm not taking into account the actual operation of a diode, but it would still be valid. And we don't use all of those methods in 321, but for an E major class, where this is spread out over an entire academic year, we actually do go over all 4, 5, 6 different methods. And we can show that using one model, I might get certain values, and those values are not far off from using a different model and a third model and a fourth model. Okay. In numerical methods, we would choose a model. We would make certain assumptions at the beginning of our analysis. Those assumptions would be based on certain logic. They'll be based on laws of physics. We would perform our calculations, and then we'd arrive at an answer. We take that answer or the solution, and we compare those values and see if our original assumptions are valid. For example, I might say that based on the circuit conditions, let me assume that the voltage is between 0.8 and 1 volt. So I would go through the solution. At the end, I might arrive at an answer of 0.6 volts. Then I would change my assumption a little bit, and I would redo my calculations. You would keep redoing your calculations until the final value fits within your assumptions. So then next I might assume that the value is between 0.7 and 0.9. And now if I get 1.1 volts, then I'm above that range. So I'm going to make a third assumption. And I would keep doing that until it fits. Okay, that approach is known as an iterative analysis. So you keep plugging away until you arrive at an acceptable value. The point is, as working professional engineers, answers are not given to you. You are the one who is in charge of determining the answers. So you would use one approach to find an answer. Then to verify that answer, you would use a second approach that can also be backed up by computer simulations. Okay, and so that's what we would do for electronic devices. And this is, of course, true not just in electrical engineering. It's valid for any engineering field or for any scientific field for that matter. Okay, so the first electronic device that we'll look at is the diode. The name comes from the fact that the first electronic device was a vacuum tube, and that vacuum tube had two electrodes in it. Two electrodes, diode. Hence the name. That's where the name comes from. Excuse me. All right, let's take a pause. Let me know if you have any questions. Okay. So from diodes, we'll go into transistors. Diodes are two terminal devices like resistors, capacitors, inductors. But transistors, whether it's a BJT or an FET or a MOSFET, they're all three terminal devices, sometimes even four. Essentially, they are three terminal devices. Okay. And then we look at op amps, operational amplifiers that are created using transistors. And then the latter half of the class, chapter 4 and 5, will be digital logic. So I borrowed this meme from Professor Chuck Bland. Really like this. He's a big fan of Star Wars and big fan of using memes. And so am I. So I borrowed it from him. Hit the ground running we shall, because the circuit analysis techniques we used from 201, they're not quite done with it yet. Y'all remember all of those? Node voltage analysis, mesh current analysis, Thevenin theorem, Norton theorem, right? All of those, we are not quite done with it. When you took 201, how many circuit analysis techniques did you learn? What if I tell you you only need three? Ohm's law, KCL, KVL. The entire course is built simply on these three equations, these three principles. Ohm's law, KVL, KCL. All other techniques are derived from these three. Your node voltage analysis is basically Ohm's law and KCL. Mesh current analysis is basically KVL and Ohm's law. Voltage division is Ohm's law. Current division is Ohm's law. Thevenin and Norton is not an analysis technique. It is a theorem that uses any analysis technique to solve for the circuit, to reduce the circuit. Okay, so the entire course is just three equations. And we will need those techniques when you study electronics. Okay, all of an electrical engineer, the entire career of an electrical engineer is built on these three equations. Everything else is derived from there. And if you want to take it back even further, all of this is derived from Maxwell's equations. Okay, you might have come across Maxwell's equations in your previous classes, but that's where it all comes from. Anyway, so coming back to our devices. So we won't go too in depth into all of those, obviously, but you would need all of those equations and the techniques from 201. So homework 1, which is for extra credit, the entire homework is extra credit, is basically a review of circuit analysis techniques. Okay. The due date, I will make it due on Sunday. Okay. So for now, ignore all the due dates that you see on Canvas. And usually it's always a rush to get all, I have like 5, 6 classes and 6 websites to set up. So just as a rush to get all the websites up and running, and then I go in and then I change all the due dates. So that's on my docket, or things of list a list of things to do either on Thursday or by the weekend. But for now, homework 1 is due on Sunday. Quiz 1 on the online quiz you'll have on Friday. It'll be something simple about circuit analysis. And then Monday we'll have a quiz in person in class. Again, that will be about circuit analysis. Okay. And so we'll talk more about that, when we get on Friday. But ignore all other due dates. Okay. So the point of this slide was, yes, we are not yet done. So you have to remember that stuff. Okay. Vacuum tubes. A bit of explanation about how the first electronic device worked. So you have two electrodes inside a sealed glass tube. Bottom one is known as the cathode. It's in close proximity to a heater. The heater is supplied with some energy from an external source, heats up, and the the cathode is made out of some conductive metal, which would emit some electrons when it gets heated. And those electrons are floating above the surface of the cathode material. Now, electrons would have negative charge, right? So what happens if you connect a plate far away let's do it this way. What happens if you connect a plate far away from the cathode to a positive charge? Electrons have negative charge. They're floating around the bottom surface near the cathode. Here you have a positive charge. What happens? Opposite charges attract. Electrons are attracted to the positive charge at the anode, and electrons start flowing in the circuit or moving. If electrons are going from left to right, which direction is current flowing? Right to left. Here we stick with the standard convention. Otherwise, we have two kinds of current flow, or references for two kinds of current flow. If you use one reference, we can say electron flow current. The other one, we can say hole flow of current. Okay. We always take current flow as the opposite of the flow of electrons, which means the current from the supply is going from minus to plus, which aligns up very well with what you learned in 201. Current always goes from high to low, plus to minus, like any other physical quantity, like water or fluid. Because of gravity, goes from high to low. Temperature always goes from high temperature to low temperature. Pressure always moves from a high pressure area to a low pressure area. Always moves, right? That's how you get wind. So current also moves from high to low, except when it's an energy source. An energy source is supplying energy. So like this power supply. So it goes for a power supply, it goes from minus to plus. Otherwise, law of conservation of energy would never work. Your circuit equations would never work. Nothing would ever work. At least mathematically, it wouldn't work. Right? So it lines up is what we have already known or established in the past. So current flows through the circuit, and that, in a sense, is the operating principle of an electronic device, like a vacuum tube. Right? These were the earliest components of an electronic circuit. There's actually computers that were built using vacuum tubes that were as large as this room. The first computer was set up, I think, University of Pennsylvania. It was known as Electronic Numerical Analysis something, ENAIC. or ENIAC. If something wasn't working right in there, it would take engineers the entire day to go in and find which vacuum tube was not working, and it would take an entire day to find the faulty part to go in and replace all the vacuum tubes that were not working. Obviously, when you have a lot of heaters in a close confined space, parts tend to go bad very quickly, right? So that was used to happen. Then after the creation of the first vacuum tube, they quickly realized they need to be able to control the flow of electrons going from cathode to anode. Otherwise, they were bouncing off the walls, highly inefficient circuit. Excuse me. And so they decided to insert a third electrode in there, right? Third electrode in the side of the walls, kind of like on the sides of the tubes. Extremely dry throat right now. So if you insert a third electrode into a vacuum tube, what do you get? 2 electrodes, diode. 3 electrodes, triode. 4 electrodes, quadrode, pentode, hexode, so on and so forth. I believe the largest number that I ever read was about 12 or 13 electrodes. I've never seen one in person. I've seen, I think, up to 6 or 7, I believe, long time ago in India. But I've only read about vacuum tubes with like 12 or 13 electrodes. There might even be higher than that, but I'm not sure about the credibility of the source. But it's all to actually, apply for different applications. Anyway, so that's basically the diode. Then you had the triode, and so on and so forth. Now, obviously, there are disadvantages of these vacuum tubes. They are large. The size of these vacuum tubes is about the size of, let's say, our fingers, and probably about a thumb. Okay, about this big. Now, in the late 1940s, around the actually, before I go here, let's talk about a little bit of history. So in the late 1940s, right around after World War II, there's a lot of research being done into semiconductor devices. And this is around 1945, 1947, I believe. 3 people at Bell Labs, 3 researchers, presented the first working prototype of a solid state transistor. Okay, so the first electronic device, the first electronic device based on a semiconductor material, like a first solid state device, was a transistor. And the names of those 3 people are John Bardeen, Walter Brattain, and William Shockley. Working at Bell Labs, and there's a very famous picture. There's a very famous image, black and white image of those 3, working in their lab, poring over their looking over their prototype device. It's become an iconic image because the entire world of semiconductors, as we know it today, that was the beginning. And the first device that they created and showed working prototype was a germanium point contact transistor. Okay. It was large in size, not so small, but it showed that you could create an electronic device without any physical moving parts. Okay, like a vacuum tube. You would not need a heater. You would not need any energy source larger than a small power supply, like a voltage supply. So these 3 were the first ones to actually present a working prototype. Going on a little bit of tangent and a little bit of history, and this invention was it had such a profound effect on everybody. or the world at large, that they were nominated for a Nobel Prize, and they eventually were awarded a Nobel Prize in physics. I think it was about 1950, I believe, 3 or 4 years later. But as it so happens, when you have people doing such high level research, there are egos that get in the way. And so what happened here with the three of them had a falling out. I think primarily Shockley, William Shockley had an issue, and he did not want to share the prize with the other two. But he was told that if you're not willing to share, then you can't be nominated, you can't be awarded. So he grudgingly had to come to the award ceremony along with the other two. John Bardeen left Bell Labs shortly after, and he went on to become a professor. I can't recall the university, but I believe it might have been UIUC, Illinois, Urbana-Champaign. And he went on to do research in superconductivity. And amazingly enough, he won a second Nobel Prize for his research in superconductivity. I think he was one of the, I guess he wasn't the first one. The first one was someone else. She was a woman from Europe. Yeah, Marie Curie. She was, I believe, originally from Poland, I believe, but she and her husband settled in France, where they were doing research, obviously with radioactive materials. They were awarded the Nobel Prize, and she amazingly won a second Nobel Prize after the passing of her husband in two different fields. Her husband had one. They set up an institute where their daughter also studied and did research. Her daughter also won. And amazingly enough, the son-in-law married to her daughter also won the research. So family of high achievers. Anyway, coming back from that tangent, as I said, Bardeen, Brattain, and Shockley had a falling out. Bardeen went on to become a professor. Brattain went on, let me say, I can't remember that. Shockley stayed, or maybe Shockley left and founded his own company, and he had a ton of engineers working for him. But he was kind of like a paranoid guy, and maybe a jerk, to put it mildly. And then a lot of engineers from there went on to, found some other companies. One of those companies was Fairchild Semiconductor. Anyone here of Fairchild Semiconductors? No. There were two people from Fairchild that left shortly thereafter to found another company. Anyone know what that company was or is? Moore and Grove, and I want to say one more person. I can't remember the name of that person. Went on to found Intel, Integrated Electronics, Intel. And it was successful for a long time, as long as engineers were running the show. But you introduce hedge fund managers in there in the management, and then Intel and Boeing, as you know, the recent troubles that are going on. I'll stop right there. So Intel Corporation, and Intel for a long time was the worldwide leader in fabrication technology. So Intel is a company that designs and manufactures their own chips. Okay, so designing a chip compared to manufacturing a chip is very, very easy. I mean, it's hard, but it's easier. Okay, you could take a computer, specialized software, learn about it. You can sit on a beach and you can do that. If you want to manufacture a chip, you need hundreds of billions of dollars just in a single factory. Each piece of equipment runs in tens of millions of dollars. Even an academic environment, if you want, and there are academic environments, Cal Poly has a semiconductor manufacturing facility. We are teaching a class this quarter. Academic clean rooms, not, Cal Poly is a smaller one, but if you go to like UCSB, UC Berkeley, where I was in Louisville, those facilities are huge. Each piece of equipment we used over there was about 1 million, 500,000, 250,000, and there's about, I don't know, 20, 25 of those in that entire facility. And that's just an academic environment. Okay, so it's very, very expensive to run. Anyway, so Intel, as I said, was the world leader for a long time. It was the only company that used to design and fabricate their own chips. Texas Instruments used to do that. National Semiconductors in Japan, you had several companies used to do that. Samsung Semiconductor is still one of the only other companies that designs and manufactures modern chips. But all other companies that you hear in the semiconductor fields, whether it's NVIDIA or Apple or Qualcomm, ARM Technologies, no one actually makes their own chips. They only design their own chips, and then they outsource it to the company, more likely TSMC or Samsung Semiconductor, to actually build those chips. Yes. So AMD was spun off from Fairchild, a lot of engineers from Intel, and the question being asked was about AMD. So AMD designed and fabricated their chips, then they split. They spun off their fabrication, which is now known as Global Foundries. So Global Foundries is basically spun off from AMD, and it's upstate New York. They have facilities all over the place, and they're the ones who actually fabricate stuff. So it's not, I don't think it's even the same company anymore. It's not in the same umbrella, as far as I know. AMD just designs chips nowadays. And so that's why they were able to make some advances in the technology and everything. Let's see. All right, so let's come back to our class. Enough about history for now. So what makes all of these companies, right? What made them? What made them was the creation of the semiconductor device. Okay, devices, electronic devices created from semiconductor material. That's what made all these companies. Okay, so let's classify materials, and what kind of materials are known as semiconductors. Broadly, we can classify a material into two categories. One, which permits the flow of current and electricity. So it permits or allows the conduction of electrons. Hence, these materials are known as a conductor. And then there are other materials that do not permit the flow of electricity or electrons. Hence, those are known as insulators. So you have conductors on the one hand, and you have insulators on the other. So conductors permit conduction of electricity, insulators do not permit. And then somewhere in the middle is a third classification, which is known as the semiconductor. A semiconductor only permits the flow of electrons or the conduction of electricity under certain conditions. Okay, under certain conditions. And there's material properties. Each of these elements have certain material properties. And the material properties we look at are resistivity, which is right, well, actually not right here, which is right here, resistivity, and there's also something known as the energy gap. Okay, so I'll talk about that in just a little bit. So what happens in a conductor versus an insulator versus a semiconductor? A conductor has a large number of free electrons. Okay, and I'll talk a little bit about the physics in the next couple of slides. And essentially, a material that has free electrons in its atomic structure, and free in the sense free to move around. Okay, free to move around. So if you apply an external energy source to this material, those electrons are already freely available. They will move in response to this externally applied energy source. And so when they move, they are conducting charge, they are charge carriers, and the movement of these charge carriers results in the flow of energy. So electrons are free to move, and electrons move in response to an external electric field. Okay. An insulator has no free electrons or very low amount of free electrons. So an insulator low or negligible amount of free electrons. Okay. There are no ideal elements in this world, right? So there's no ideal insulator or no ideal conductor. Every conductor will also have certain resistance. Every insulator also has certain conductivity, but it's not useful. You cannot use them for those purposes. So an insulator will have low or negligible amount of free carriers. And then we have the semiconductor. Semiconductor will have low number of free carriers, but not as much as a conductor. Okay, it'll have enough to conduct electricity under the right conditions. Okay, and even then it would be a push. So more than an insulator, but far less than a conductor. Okay, the conductivity is based on the number of electrons and holes, and we'll talk about that shortly too. Okay, so conductors have a large number of free electrons, insulators have a very low number of electrons, and semiconductors are somewhere in the middle. Okay, semiconductors are somewhere in the middle. So the more number of electrons you have available, the lower your resistivity and the higher your conductivity. Resistivity is a material property. Conductivity is the opposite. Resistivity is rho. The Greek letter rho, R-H-O. Again, we won't go into that physics. So if you look at this table, you look at these materials right here. Resistivity around room temperature is measured into 10 raised to minus 6, 10 raised to minus 7, 10 raised to minus 8. Very, very low. Conductivity, which is the opposite of resistivity or reciprocal, very, very large, right? 10 raised to 6, 10 raised to 7, 10 raised to 8. And then right here at the bottom, we have our semiconductors. Okay, we have germanium, we have silicon, and we have something known as a compound semiconductor, which is gallium arsenide. And again, that's a discussion for later. Okay. So one of the questions that might come to mind is, how come silicon's resistivity is so large and still be considered a semiconductor? Well, that's where the physics comes in. Okay. So I won't go too deep into it again, but let's start with the atomic structure. We have an atomic structure. What is common to both silicon and germanium in terms of the number of electrons? The outermost shell, same group, yes, column 4 of the periodic table. So you have an atomic structure. You have electrons that are orbiting around the nucleus, and each of those are fixed. At least that's what the latest model is, right? So they are fixed and they have a fixed energy level. Okay, but the energy in these electrons does not exist in infinite levels. They are discrete levels. They are quantized. And so each orbit or each electron is occupying an energy level that comprises a certain band. And so you get different energy levels and different bands of energy. And if you plot a two-dimensional diagram of those energy levels, we get what is known as the energy band diagram. Okay, energy band diagram. You all with me so far? Okay. In this energy band diagram, without making it too complicated, we look at two things: valence band, so valence band energy, and conduction band or conduction band energy. The outermost shell of an atom is known as the valence shell, the valence band. The electrons that are occupying in there are known as the valence band electrons. They have the valence band energy. And in silicon and germanium, as you said, are from column 4 of the periodic table. So they have 4 electrons in the outermost shell. You need 8 electrons to form a covalent bond and a stable atomic structure, right? So we have the energy band diagram. And in that energy band diagram, if I plot a two-dimensional level, we have the valence band right here, and you have the conduction band right here. That's conduction, sorry. And if an electron in the valence shell acquires enough energy, it can jump from the valence band to the conduction band. Okay, so it can move from here to here. And now it's it's available to move in the atomic structure, meaning now it is available, it's free to move and it's available to conduct electricity. Okay, that energy can be acquired in multiple ways. You can have photons coming onto your semiconductor material, acquires enough energy, electrons start flowing. That's how you get a solar cell. You can heat it up, meaning thermal energy. You acquire energy from heat, thermal energy, and you're now able to break free of your bonds and again be free to conduct. Or you can apply an external energy source like a voltage or a current, an external electric field, and acquire that energy. So multiple different ways. Okay. The gap between these two is known as the energy band gap. Okay, energy band gap. And this is the other critical property of the material. For silicon, for germanium, this energy band gap for silicon is 1.12 or 1.1 electron volts. So in addition to having 4 electrons in the outermost shell, the energy band gap of silicon is 1.1. It's small. For metals, there is no energy band gap. It overlaps because they're always free electrons. Yes. That's basically a material property. That's the established material property. Like how resistivity is established, that's how it is. Germanium is, I believe, I can't remember the exact number. There's one other element, one other very common element that has 4 electrons in its outermost shell. And you don't see it here. Anyone? Carbon. Carbon has 4 electrons in its outermost orbit, but is not classified as a semiconductor. The reason is carbon's energy band gap is about 6.3 electron volts. It's very high. It's insurmountable. Carbon by itself is not classified as a semiconductor because the energy band gap cannot be overcome by any known laws of physics, basically. So resistivity and the energy band gap, these are the two important ones. And we won't go much further than this. Any further than this, then we are studying EE 524, graduate level solid state electronics. Okay. But these are the two things to keep in mind: resistivity and energy band gap. All right, let's take a pause. Let me know if you have any questions. So far, so good. Okay. All right. What is absolute zero? I should say, what value is absolute zero? Temperature on the Kelvin scale. Absolute zero is 0 Kelvin, which is minus 273 degrees Celsius. Okay. Meaning if I was silicon or any material, it's so freaking cold, I can't think, I can't move, I can't do anything. I'm just frozen solid. Okay. Minus 273 degrees C. So if you're a semiconductor like this, and silicon is by far the most common semiconductor, so we'll stick with silicon. You have an atomic structure where you have electrons, 4 electrons in your outermost shell, and you share 1 electron each with your neighboring atoms. So each silicon atom shares 1 electron with its neighboring atom, and that allows it to create a very stable structure with covalent bonds between all of those atoms. Okay, so each one of those bonds is known as a covalent bond. It's a stable atomic structure. Each atom now has 8 electrons orbiting around its nucleus. Okay, at absolute zero, all of these bonds are frozen in place. There's no energy available whatsoever. As the temperature rises from 0 Kelvin, from 0 to 10, 20, 50, 100, 150, 200, as the temperature rises, you now have thermal energy. The electrons, some of these electrons will acquire enough or sufficient thermal energy to break free of these bonds. Okay, they will break free of these bonds, and at room temperature, which is 273 degrees, sorry, not 270, accepted values for room temperature is 300 Kelvin. It's about 27 degrees C, which is about 54 plus 32, it's about 80 degrees Fahrenheit. Okay, quick conversion between Fahrenheit and Celsius. It's about 80, 85 degrees Fahrenheit. You have some electrons, not all of them, very low number of electrons that have broken free from their covalent bonds and are now free to move about and conduct. Okay, and so this at room temperature, some electrons break free of their bonds and are available as free charge carriers. Okay, so at room temperature, semiconductors have free electrons available for conduction of electricity. It won't be good, it won't work, but they are available. So they are intrinsic to the material. And hence, these are known as intrinsic semiconductors. And so, an intrinsic material will have some charge carriers that are available for conduction of electricity. And going forward, we'll look at how we can introduce more free charge carriers in there to create a conducting material out of a semiconductor. Okay. Just one final thing I'll write is at absolute zero, which is 0 Kelvin, Actually, it's not okay, is 0 Kelvin, no free carriers, no broken bonds. Okay. All right, we'll end class here today and we'll pick up here again on Friday. There'll be a offline quiz on Friday. And since it's the first time, I'll give a longer time for students, and maybe I'll give 2 or even 3 attempts to get it done. Okay. So that everybody gets used to the system in the first week, and then going forward, going forward will be a little bit more stringent. So it'll be mostly a review of circuit analysis. So again, get started on homework 1 if you have not yet done so. It's a review of 201. The quiz on Friday will also be based on some circuit analysis. All right.